So you had a long break for 1 week, and no. Do you have class yesterday? No? If no, you have 8 days, a long break, and I think you must fresh up again. So, I mean to talk about something that then cheer up you guys and me, and then start the class. But I find some of you copy homework and doing homework on the class just a little bit frustrating.
How was your holiday?
Home was my holiday.
Yeah.
I'm good, but I'm not good now.
Yeah. It's really frustrating.
I had a rest for only 2 days and worked for another 5 days. From morning 8, it's just like a normal day for us. Work from 8 to 10 on the evening. Yes, 10 p.m. A lot of work. You may think that university staff is a very good job, it's a very nice job, but as long as you're doing research and teaching, our job is not about teaching. It's not about teach undergraduates, research master students, and also about research. So what that means? That means so the university have some requirements for you to go to a promotion. As long as you meet the requirements, you have the opportunity to go to a promotion. But everyone knows those requirements, so they reach a very higher one. And because the promotion, for example, each year we have just 2 people got promotion. So it's not like that you finished, you got all the requirements, then you can got promotion. No. You must to be the first or second one, then you can got the promotion. So this is the situation in China for every job, I think.
You will get the festival.
Pardon? Festival?
You will get the promotion. You will get the promotion.
Really?
Yeah.
Yes.
Maybe it takes time, but yes, I will. So, in last class, we actually introduced the main thing in chapter 4. In chapter 4. And we talk about the liquid limit. Actually, in chapter 4, we have 3 limits to introduce and how to go to those limits in laboratory. That was plastic limit, liquid limit, and shrinkage limit. So from shrinkage limit to liquid limit, the water content is actually increased, right? It's getting higher and higher. So soil getting from a solid to a mid-solid, and then mid-liquid, and then liquid. So as the water content increases, so actually the phase change. So at exactly water content, for example, from solid to the semi-solid, we call this water content a shrinkage limit. From semi-solid to plastic, we call this water content a plastic limit. And the same to the liquid limit. So this is a definition for these 3 limits. And then we talk about some laboratory methods, how to go to liquid limits, plastic limits, and shrinkage limits. For the liquid limit, we introduced 2 methods in laboratory. One is percussion cup method. A percussion cup is such a device that you can make a soil pass in the cup and then make a groove in the middle. The groove have exactly depth and width because we have such a tool. We have such a tool, grooving tool, to make the groove. So as long as you handle this stuff and then run to the car, as long as the groove start closing, then the water content start closing at a handling of 25 times. Then the water content for the past now is a liquid limit. This is the percussion cup method. But the most we use is the four-core method in here. With four-core method, we actually can got a liquid limit and plastic limit with just at the same time, right? With a set of tests, then you can got both liquid limit and plastic limit. This is why the four-core method is widely used all over the world to get to estimate the plasticity of soil. This is four-core method. So in here, for the both laboratory test method, what you need to learn is if the problem gives you just a number, for example, gives you the moisture content and the penetration, for example, for four-core method, gives you the moisture content and penetration, you can analyze where is the liquid limit. And as long as it gives you the plastic limit, you can calculate the plastic index, right? So then what is plastic index? Plastic index is the difference between liquid limit and plastic limit, right? As long as you know these two, then you got plastic limit, plastic index. Plastic index is a very important soil parameters to classify fine-grained soil. Because for clay soil or for gravel, for clay soil, for sand, so for those soil, we didn't use plastic index for those soil because plastic index is an only parameter for fine-grained soil, for clay, right? And then we talk about shrinkage limit. We said that shrinkage limit we can estimate with laboratory test. Just dry soil and measure the volume and mass of the soil before and after drying. But we said that use this equation, it is actually difficult because the volume change is difficult to estimate, right? So you just know what is shrinkage limit. We don't have to calculate the shrinkage limit. It's not as very common as liquid limit and plastic limit. And we introduced the liquidity index. Liquidity index is calculated. We use this equation. In here, the bottom number in here is actually plastic index, and the top one tells you the difference between the current water content and plastic limit. This is liquidity index. It actually tells how wet the soil now, right? It tells you the relative position to the plastic limit and liquid limit for the soil now, right? For example, if the water content is in here, so the liquidity index is between 0 to 1, right? Because water content now is higher than plastic limit but lower than liquid limit. So this value is positive, but it is smaller than this value. So the ratio in here now is from 0 to 1 in here. But if the water content is higher than liquid limit in here, so the liquidity index is higher than 1, right? Because the top number in here, water content is higher than liquid limit. So this part is higher than this part. So the ratio is higher than 1. Actually, the liquidity index tells you the relative how weight of the soil now compares to the plastic limit and liquid limit. As well as the consistency index, it is actually the same. with that liquidity index. And then we stopped here in last class. Then let's talk about activity. Activity is not quite easy to understand. And I think it is a little bit early for you to understand the activity. Or something like a charge on the clay particle. So you just know those things, that's all, right? If you work for a master degree or PhD, then you may need to understand what is the activity of soil, what is the structure, what is very deep stuff, very microstructural stuff. So activity, we use A, parameter A to represent it. Activity is used as an index for identify the swelling potential of clay soil. Actually, it's not only swelling potential, but actually something else. Activity, how to say? It is a very, it's very hard to say. It's related to a lot of things. Those things, it's not like a liquid limit, plastic limit. We can use a parameter to represent it. I just want to say it is not only related to swelling, but other properties, microstructure properties of soil. But how to estimate activity A? Activity A, we use the ratio, such a ratio to estimate activity. The top number in here is plastic index. That is the difference between liquid limit and plastic limit, right? So the plastic index for most of the soil, it is between 10 to actually 25, something like this. And the bottom number is the percentage of clay size friction by weight. In here, by weight is just to say that the friction is by weight. For example, we learned the particle size distribution curve. The y-axis is by weight, right? The percentage is got by weight, the ratio between weight. So in here, by weight means that the friction is calculated by weight, similar with particle size distribution. For example, as long as you got a particle size distribution, if you got a standard, for example, we say that clay particle is usually, in China, we say clay particle is the soil particle less than 0.005 millimeter. But in most countries, in most European countries, clay particle is particle diameter less than 0.002 millimeter. But 0.005 is close to 0.002. So actually there is not much difference. And actually in China, the newest code, you adopt 0.002. So as long as you got particle size distribution curve, so the percentage less than 0.002 millimeter gives you the friction of the clay, right? And if you know the plastic index of soil, you can go to the activity of such a soil. And in here, keep in mind, activity, we just say to clay soil. Or soil, for example, silty clay, yes, we can say it is also a kind of clay. In most cases, we say it is for fine-grained soil. And the relationship of the plasticity index to the percentage of clay size friction may not always pass through the original origin. So A may be defined as such an equation. So what that means? You see that in here, you see, so it is a ratio, right? And for example, for an equation for a line, you say, for example, y equals ax plus b. This is a very normal or very common equation for line. But when you say y equals to ax, that means b equals to 0, so the line must pass 0, point 0, right? So this actually is the equation in here. It's actually now, for example, the x actually equals to a, and y actually equals to clay size fraction by weight. For example, we can say x equals to, no, we can say that a minus fraction equals to pi, because pi actually it is a constant value. I mean, these two is actually can transform, but usually this curve or the relationship between pi and the clay size fraction is not past 0. It is a line past some points in here or some points in here. So it is like this, or it is a group of line past this, past the point in this, at here. So it is not always past 0. This is why we have a C dash value in here. So C dash is a constant for given soil. This is not quite important in here. And then let's say the activity actually is not a constant value for a given soil. For example, the relationship of the plasticity index and the percentage of clay friction. We said that it is a ratio, right? But it is not a constant ratio, it is change. So, for clay size friction greater than 40%, the straight line passes through the origin. For example, for the percentage of clay size friction higher than 40%. So then now the plastic index is past 0, so this ratio so the ratio now for this line is a constant value. But as long as the percentage of clay size friction less than 40%, it is changed to another ratio. So it is not always a constant if the soil if the clay percentage increase, it is not always a constant. It may also change. And then let's see. In here is just to introduce the activity of clay soil. We not always use it. But plasticity chart is a very useful chart. So this chart tells you the how to classify a clay soil with liquid limit and the plastic index very quick. So we usually use this plasticity chart. The plasticity chart plots the liquidity limits against the plasticity index of various soil. The information provided in the plasticity chart is useful for studying the correlation of these parameters and for soil identification. Actually, in most cases, we use this to do the soil identification. So, what's this chart? In this chart, you see we have 4 lines. The first line, we call it is U line. The bottom line in here, it is a E line. And we have a vertical for the liquid limit at 30 and liquid limit at 50. Right? We have these 4 lines. These 4 lines actually separate this chart into 1, 2, 3, 4, 5, 6 parts. And 6 parts represents different soil. And in here, this is cohesionless soil, that is care soil, right? Cohesionless actually means soil have no cohesive, and soil is in most cases sand or gravel, or have no too much clay particles. For example, the clay particles less than 5%. but the bottom part, the bottom part below the U line is for cohesive soil, and we separate into 6 parts with these 4 lines. The U line, the equation for U line is this, and the equation for A line is this. So as long as you know these 2 lines, you can draw the plasticity chart, right? Because in here this is 30, in here this is 50. You can know the position of these 4 lines, then you can draw the plasticity chart. And how to use this chart? As long as you go to a soil, right, you know the plastic index and you know the liquid limit, then you can fix the soil position on this chart, right? For example, let's say the liquid limit, let's say it is 36, and the plastic index is, let's say, 18. So 36 is something around here, right? And 18. So the position of the soil is at here. Then let's say for this kind of soil, it should be, wow, it should be in organic clays of medium plasticity. So this is how to use the plasticity chart to do the soil identification. You can give a very brief description for this kind of soil. This soil is inorganic clay, medium plasticity. Right? This is how we use. Excuse me. Okay? Yeah. Oh. Okay.辛老师吗？我也感觉，好的，行。好的，行。好的，我明白了。就是以后这个结构力学是不是可能还会再分出来班？因为之前是不愿带这门课，然后不愿走了之后，我们是。可以分成4个班的，因为我感觉以后我们像今年大一的200多个人，好的，我明白了。好的，行，没问题。好的。Sorry. So this is plasticity chart and how we use this chart to do soil identification. As long as you know the plasticity index and liquid limit, then you can fix the soil on the position of the soil on this chart, and then based on this, you can tell, give a very brief description of the soil. And as long as you know the as we introduce a plasticity chart, then we can estimate the shrinkage limit from the plasticity index and liquid limit in liquid limit. So this is a plasticity chart, right? We know U line, we know A line. For example, you have a soil at the position of A. So plot the plastic index against the liquid limit of a given soil A, such as the point in this figure on the right. For this soil, the liquid limit may be 67, and the plastic index may be around 20. So you can fix the position of the soil A, right, on the plasticity chart. If we go back to the chart in here, so this soil, actually, it is an inorganic silt of high compressibility, or organic clays. So for this kind of clay, it is very organic. Organic means the clay friction is very high in most cases. And if you fix the position of the soil at point A, then project the A line and U line downwards to meet at point B. So first project the A line and U line and downwards, and let them meet at this point, and then connect point A and point B. It must have a coarse point at x-axis, right? At around point C. So the water content at point C gives you the shrinkage limit of this soil. So now you know the plastic index, liquid limit, and shrinkage limit, the three limits of the soil. This is how to use the plasticity chart to estimate the shrinkage limits. It is a very rough way, because we say shrinkage limit, and it's difficult to estimate in laboratory. And this is something about the activity of the soil and some very description or introduce the plasticity chart. And then let's see soil structure. Soil structure is actually very important to soil, because the behavior of the soil, or let's say the mechanic properties of the soil, actually, it is a reflection of soil microstructure, right? If the soil have a very large void, for example, in here. So here I show four different, let's say in here, four different kind of soil. You see, the microstructure actually different, right? So the property different. So you're doing some tests, laboratory tests, and you find that, okay, the compressibility is different, the shear strength is different. But why they are different? Because the original microstructure, the arrangement of those particles and the cohesive, all the contaction between the particles is different. So these are called microstructure. So how the particles arrange each other, how the aggregates, or how big of the aggregates, and how to say the contaction is point contact or phase contact. Those are all called microstructure of the soil, and they influence the macro property of the soil. Let's see some structures. So soil structure is a geometric arrangement of soil particles with respect to one another. The factors that affect soil structure are shape of shape of the particle, size of the particle, mineralogical composition of soil particle, nature and composition of soil water. So that is most effects, most factors are all from particles, right? Particles shape, particle size. If it is a shape like, how to say, it's a have sharp ends, all the shape of the particle is just a round shape, right? Or the size, for example, we have clay. Clay is a quite small particle size, but sand is in a large particle size. So the arrangement between sand particles and clay particle will form different soil structure. Mineralogical composition of soil particles. This means that if mineral, we say minerals, three main minerals are maintenance, right? Illite and kaolin, right? So if maintenance is in a higher percentage than kaolin, then the soil shows a large swelling property. Okay, so mineral is also very important to influence soil structures. And then the natural composition of soil water. That means the liquid phase in the soil also affects soil structure. If the soil water is a pure water or the soil water is salty water, it also has some influence on soil microstructure. And actually there are two main classification groups for soil. The first group is cohesionless soil. Cohesionless soil, we said it is kelp soil, right? All soil have no too much clay particles. All cohesive soil, that is clay soil, fine-grained soil. Then let's see the soil structure for those two different kinds of soil. The first is a single-grained structure. Single-grained structure, you can in most cases you can find such a soil structure in cohesionless soil. For example, in sand. In single-grained structure, soil particles are in stable position, with each particles in contact with surrounding waste. So this is a single-grained structure for cohesionless soil. For sand is usually just the particles distributes like this, a single-grained structure. But the void ratio for a single-grained structure of soil, it varies with the densities of packing. For example, the void ratio for such a distribution of soil particle is different with such a distribution. So this depends on how the orientation of the particles, how arrange those soil particles. And another soil structure is honeycombed structures. This is not only for cohesionless soil. Honeycombed structure have large void ratio and can carry out ordinary static loads. For example, in here, this is soil solids, this is the particle. Now the particle have some cohesion between each other. We say that as long as soil have fine particles, for example, have clay, have silt, we say the clay have charge on the surface and attract particles and water as long as another phase have charge, right? So this is why for fine-grained soil or cohesive soil, particles can connect to each other. It can attract each other and attach each other together like this and formed a shape like a honeycomb. So this kind of structure called a honeycomb structure. So particles attach particles and form a large void in here. And such a structure actually can carry a load. So for soil, actually, for such a soil, For soil with such a structure, actually it have a higher yielding pressure. You need to apply a higher load, then the soil structure may collapse. So it said under a heavy load or when subject to shock loading, the structure breaks down, resulting in a large amount of sediment. So this is the honeycomb structure. Have a break.